Welcome to Types of Mass Spectrometers. So, the mass spectrometer that we've examined thus far is called a magnetic sector mass spectrometer. And again, you can see that over here. Now, ions with constant kinetic energy, but different mass, are separated by their trajectories in a magnetic field. And so we've got our ions coming out of our ion source. They pass through the magnetic field generated by our magnet here, and then they're separated by mass to charge ratio as they travel down the tube and strike the detector. So the kinetic energy is given to our ions via the voltage difference between the acceleration plates and the ion source. So again, you can see the ion source over here, and we have our ion acceleration plates here and here. But the actual kinetic energy of the ion depends upon exactly where in the ion source the ion was formed and upon how much kinetic energy the neutral molecule had before it was charged, before that neutral molecule was ionized. Now remember that at any temperature, the molecules in a sample have some range of velocities. All of those molecules are not traveling at the same speed. And thus, in our ion source here, we have some molecules that are closer to the ion acceleration plates. We have some molecules that are farther from the ion acceleration plates. And because the electrostatic attraction or repulsion from those plates is going to depend on the distance of that ion from the plates, then where in our source the ion is when it gets charged will affect the speed with which it leaves and how much kinetic energy that neutral molecule had before being ionized will also affect it. Because if the neutral molecule had some kinetic energy beforehand and then we're accelerating it, the total kinetic energy that it has after leaving the source is a result of the kinetic energy that it started with plus the acceleration that it was given from the ion acceleration plates. So the resolving power of a mass spectrometer then is limited by the range of kinetic energy of the ions, which is typically around 0.1% or so. Now this variation leads to a resolving power of around 10 to the 3. This is a resolution of 0.1 at a mass to charge ratio of 100. Now we can improve the resolution by using a double focusing mass spectrometer, which has an electric sector added to the ion path prior to the magnetic sector. So essentially, only those ions with a small range of energies are passing the exit slit and entering the magnetic sector, and then get separated by the magnetic sector as well. So you can see here, we've got ions coming in from our ion source, they're passing through some small entrance slit, and here we have the electric sector, so we have some positive charge down here, a negative charge up there, and that means that cations with low kinetic energies are going to tend to be towards the top here, and ions with larger kinetic energies for the same mass to charge ratio are going to be farther to the bottom here. And so now we have some exit slit there, and then only those ions with the kinetic energy that we're trying to select for get then passed to our magnetic sector. So this process decreases the variation in kinetic energy amongst our ions, and this decreased variation then leads to a resolving power of closer to 10 to the 5, and this means a resolution of 0.001 at a mass to charge ratio of 100. Another quite common type of mass spectrometer is the transmission quadrupole mass spectrometer, and here our transmission quadrupole mass spectrometer can be connected to the outlet of gas chromatography column in order to record the mass spectrum of eluents exiting that column. So, species that exit the column, they're coming off the column and then they're entering the mass spectrometer here. So they're entering the electron ionization chamber, which is contained at this portion. And that chamber is under vacuum at around 10 to the minus 4 pascals, which is roughly 10 to the minus 6 torr. So the ions in the ionization chamber here are then accelerated by something like 5 to 15 volts before they're entering the quadrupole filter, and the quadrupole mass separator is in here. So our quadrupole consists of 4 parallel metal rods that you see here, 1, 2, 3, and 4. And onto these metal rods is applied a constant voltage and an RF oscillating voltage. So remember that RF is the radio frequency. So we've got the superposition of our oscillating voltage on top of a constant voltage, and that allows our ions to then oscillate back and forth, and those ions with the correct mass to charge ratio that we're selecting for can make it through and then pass through the exit slit. Those that don't have the correct mass to charge ratio have an unstable trajectory in here and eventually collide with one of our rods or get exited from the region between those four rods. So again, the electric field between the rods deflects ions in complex trajectories as they're moving from the ionization here towards our detector over on the right, and only those ions with the desired mass to charge ratio pass through to our detector. So the quadrupole mass spectrometer is fairly cheap, and thus it's fairly common. It's also able to record somewhere between 2 and 8 spectra per second, and can cover a range of up to about 4,000 AMU. So the resolution of a transmission quadrupole mass spectrometer is typically sufficient to resolve peaks separated by about 0.3. And note that while magnetic sector and double focusing mass spectrometers act at constant resolving power, the quadrupoles are operating at constant resolution. That is, in the magnetic sector and double focusing mass spectrometers, separation between peaks decreases as mass to charge increases. But in the quadrupole mass spectrometer, the separation of peaks remains constant as the mass to charge ratio changes. So note that the figure shown here, over here, shows not a discrete-dynode detector as we've shown previously, but a high-energy dynode and a continuous-dynode electron multiplier. So we have down here the high-energy dynode, and up there this continuous-dynode electron multiplier that looks sort of like a cornucopia. So this system is used to give approximately the same response per ion, regardless of the ion mass. So ions that are transmitted through our quadrupole and leave the exit slit here are accelerated towards our high-energy dynode over here, and those ions then cause the emission of electrons from our high-energy dynode. Those electrons then travel up into our continuous dynode. So our continuous dynode electron multiplier is made of lead-doped glass, which is electrically resistive, causing the voltage at the mouth over here, this is around -2 kilovolts, to decrease to ground over here towards the point. And electrons that are liberated from the continuous dynode then are traveling towards the more positive narrow end, which is over here. So those electrons bounce back and forth, and every time they bounce, they're releasing additional electrons. Then those electrons continue closer to the narrow end, and so on. And so each electron that enters our continuous dynode here causes something like 10 to the 5 electrons to strike our detector over here at the narrow end. Another type of mass spectrometer is the time of flight mass spectrometer. And this uses the time that's required for ions to travel from the source to the detector as a way of separating ions with different mass to charge ratios. So here we have a diagram showing a time of flight mass spectrometer, and the backplate, which is over here, periodically repels ions with a voltage of 5,000 volts, and by periodically we mean someplace between 3 and 20 kilohertz. So somewhere between 3,000 and 20,000 times every second we've got ions being accelerated down our drift tube. So those ions travel through the first drift region that's in here, and in that region there is no electric or magnetic field, which means there is no acceleration on those ions. So assuming that all the ions have the same kinetic energy, then their velocities vary according to the kinetic energy is equal to 1/2 mv squared, and that means that lighter ions will be traveling faster. And of course, because they're traveling faster, then they'll strike the detector first. So, for a simple time-of-flight mass spectrometer, a straight tube with a detector at the end is sufficient, because lighter mass ions strike the detector first, followed by the heavier ions. But the variation in kinetic energy of the neutral molecules before ionization and the variation in ion acceleration due to position within the ion source will cause these ions to be badly spread out by the time they strike the detector. So ions formed near the grid will be accelerated for a short period of time before they leave the source, whereas ions formed near the backplate are accelerated for longer periods of time before they leave the source. And this increases the spread in the actual kinetic energy of the ions leaving the source, and thus the resolving power will be fairly low. But the resolving power can be improved by using a reflectron. So the reflectron is composed of a series of ring-shaped electrodes that we show here. And each of those electrodes is held at successively higher voltage, followed by a grid back here at some voltage that is higher than the voltage applied to our backplate. That is, as the ions enter the reflectron, then they're gradually slowed down, and then they get reflected and they pass back down the drift tube again. Now, we have to have a higher voltage on our grid back here than we had over here on our backplate, because the voltage on that backplate determines how much kinetic energy those ions have, and if we want to prevent any of those ions from passing this point, then we need to have a higher voltage here than we had over there. So again, the voltage on the grid over here has to be higher than the voltage applied to our backplate over here in order to ensure that the ions never actually reach the grid itself, or they'll strike the grid and be lost. They won't travel back down and strike our detector. So let's examine two ions that are expelled from the source at different times and with different speeds. One ion is formed near the grid over here, and it's going to be expelled first. That is, it has a lower than average kinetic energy. Our other ion is going to be formed nearer the backplate, and it's going to be expelled later. That is, it's going to have a higher than average kinetic energy as it travels down the drift tube. So our faster ion, formed near the backplate, will overtake our slower ion at what's called the space focus plane. Now note that the distance between the grid and the space focus plane is twice the distance between the grid and the backplate. Also note that all ions of a given mass will arrive at that space focus plane at exactly the same time. The distance between the space focus plane and the grid is twice the distance between the backplate and the grid. So the faster ion then continues ahead of the slower ion once it passes the space focus plane, and when those ions then reach the reflectron, they decelerate and then they accelerate in the opposite direction. And note here that the ions leave the reflectron with the same kinetic energy that they entered the reflectron with, but the faster ion requires more time to decelerate in the reflectron, and thus it's going to leave the reflectron after that slower ion did, even though it arrived sooner. And then our ions travel back down the second drift region, and when our ions reach the grid in front of the detector, then they've again reached the space focus plane, because note that the grid here is at the same place as our space focus plane was up here. And that means that all of the ions of a given mass will arrive at our grid at the same time, regardless of their kinetic energy. The reflectron can improve the time-of-flight mass spectrometer resolving power to 10,000 to 25,000. So this is a separation of around 0.001. So the time-of-flight mass spectrometer can collect many spectra per second, somewhere between 100 and 10,000. It can measure very high masses, up to 10 to the 6th. But the time-of-flight mass spectrometer requires a lower pressure. This is something like 10 to the minus 9 torr. And this is ultra-high vacuum. So the time-of-flight mass spectrometer requires a lower pressure than the transmission quadrupole and the magnetic sector mass spectrometers, because those each require 10 to the minus 6, or just high vacuum. So chromatography mass spectrometry often uses a three-dimensional quadrupole ion trap mass spectrometer. And in this spectrometer, which we've shown over here, we have species leaving the chromatography column that enter the three-dimensional ion trap from the outlet at the lower left down here. Our molecules are then ionized when the gate electrode periodically allows electrons from the filament, which is up here, to pass through into the ion trap cavity, which is in there, via holes in the end cap. So we've got electrons that come out through these holes there when that gate electrode allows them through. And a constant frequency RF voltage applied to the central ring electrode, which is here and there, causes those ions in the middle there to undergo stable three-dimensional orbits within our cavity. And note that the lower the mass to charge ratio of the ion, the farther out the orbit is. That is, the larger the radius of the orbit. So as the amplitude of the RF voltage is increased, the orbits of our ions will destabilize, starting with the lowest mass to charge ratio, because those are the ones that are farthest out. And those destabilized ions that then exit the cavity through the bottom here, through holes in the bottom end cap, can then be detected by the electron multiplier down here. So they'll strike our high energy dynode there, and then those electrons can travel in to our continuous dynode electron multiplier over here and strike the detector down there. Note that the other half of the ions are going to go up and exit our ion trap cavity through that top end cap. So the resolving power is somewhere between 1,000 and 4,000, and the accuracy of our mass to charge ratio is about 0.1, and the maximum detectable mass to charge ratio is around 20,000. And note here that the sensitivity is also quite high. It's somewhere between 1 and 10 picograms. And this high sensitivity is coming about because half of our ions are reaching our detector, and then half are exiting through the top cap. And in most other mass spectrometers, there's a much smaller fraction that strike the detector. Another type of mass spectrometer is called a linear quadrupole ion trap mass spectrometer. And this traps a higher fraction of ions and can store more ions than the three-dimensional quadrupole ion trap can. So if we take our transmission quadrupole mass spectrometer that we have here, and then we add sections here and there on either end of our rods with higher potentials applied to them, then we can create a potential well that will trap our cations. So you can see here we have a higher potential, and then it drops down for the majority of that rod, and then we have another cap at the other side that is giving us now this potential well, and we have our ions that are trapped between these two regions of higher potential. And the linear quadrupole ion trap has a larger capacity because it's just physically larger, and thus it can trap more ions, so something like 30 times more than the three-dimensional quadrupole ion trap. And combined with the increased trapping efficiency, then this increases the sensitivity of our linear ion trap by an order of magnitude relative to the three-dimensional ion trap. So up until now, all the mass spectrometers required a magnetic field or an RF field. But the Orbitrap mass spectrometer does not require either of these. So we have a diagram of the Orbitrap mass spectrometer here, and our two outer electrodes, which are here and there. We've got two halves that are isolated electrically from one another, and they're kept near the ground. And the central electrode, which is this electrode in the center there, that electrode is kept at minus 5,000 volts. So these potential differences between our outer electrodes and our central electrode cause the electric field perpendicular to the central electrode near its center, here, this direction. But near the outside, we get sharper and sharper angles that are pushing the ions in. So this electric field then causes our ions injected into the Orbitrap to oscillate back and forth between the left and right halves. And this oscillation frequency then is proportional to the inverse of the square root of the mass to charge ratio. So these oscillating ions cause an image charge on the two outer electrodes. So the image charge is opposite in charge. That is, because the ions injected are cations, then the electrons are attracted to the surfaces of our electrodes. So we've got cations oscillating back and forth in their orbits from the left half to the right. And on the surfaces of those electrodes here, for the left half and there for the right half, we've got electrons that are attracted when the ions are closer to that half, and then attracted to the surface of the other electrode when the ions are on the other side. So an amplifier that is connected to our two halves measures the image current oscillating between the two electrodes, and the Orbitrap contains ions of different mass to charge values, and each of these will oscillate at a different frequency, and thus the amplifier is measuring the sum of the currents from all the mass to charge values, and we can then decompose the current into its component frequencies using a Fourier transform. This was discussed in Chapter 19, Section 5, and the frequencies then allow us to identify the mass to charge values of our trapped ions. Another technique is called ion mobility spectrometry, and ion mobility spectrometers are often used at airport security checkpoints to detect banned substances. Now note here that ion mobility spectrometers are not mass spectrometers, and they do not measure molecular mass or provide any structural information to us. So electrophoresis, which is discussed in Chapter 25, uses an electric field to cause the migration of ions in a solution. But ion mobility spectrometry is essentially gas phase electrophoresis. That is, the separation of ions is occurring using their size to charge ratio. Not mass to charge ratio, but size to charge ratio. Note here that ion mobility spectrometry is able to separate isomers. So, a cotton swab containing a sample is placed on the heated anvil over here to the left. The analyte that is desorbed from that sample travels up and into the instrument with a carrier gas that's composed of dry air and a chemical ionization reagent. That reagent is generally chlorine for anions and ammonia or acetone for cations. So the gas then passes through a tube containing the radioactive nickel-63. So we have that here. We've got that tube. And as that gas passes through, the nickel-63 is emitting beta particles. Remember that these are electrons. So the beta particles are ionizing the reagent gas, which then reacts with our analyte to create analyte ions in the gas phase. And a gating grid then allows a packet of ions into the drift tube via a short voltage pulse of something like 250 microseconds. So we've got our gating grids here that allow small pulses of ions through. And the pressure in our drift tube here is atmospheric pressure. We don't have to keep this at vacuum or high vacuum or ultra high vacuum. So our ions are then accelerated down the drift tube via a large voltage of 200 to 300 volts per centimeter. And as the ions drift down our drift region here, the larger molecules are retarded by collisions with the drift gas. And that means that these smaller ions reach the detector over here on the right faster than the larger molecules with the same charge. So the detector response as a function of drift time then allows us to plot a spectrum of sorts of size to charge ratio for the analyte ions. So that was types of mass spectrometers.